Swayam Prabha. Digital India. Educated India.
Alright, so let's get started with today's class. So the plan today is to move on from the very basic cryptographic primitives that we saw last time, one-way functions and so on. What happened? Okay. So moving on from the basic things that we saw last time to something which was a really important discovery in computer science, and that is the notion of public key encryption. So as I already discussed with you last time, that it should exist is something that is that was very surprising at the time that it came out. And what really is our confidence in the fact that it exists? Actually, the confidence is not based on any rigorous proof. So we conjecture that these candidates for public key encryption that we have are secure, but we don't have any proof. The proof that we have is that breaking it is at least as hard as breaking some assumption like factoring or discrete log or one of the other assumptions that we saw. Okay, so let's start by defining this object, and then we will see two constructions today. One will be using the decision Diffie-Hellman problem, which we defined last time. We can recall what it is again, and the second one is the RSA. Okay. So public key encryption. Okay, so let's see. So what do we need in order to define a public key encryption scheme? So we need two things. One is that of course we need to specify the algorithms, right? So there should be, is this working? Okay. So there should be like an encryption algorithm, a decryption algorithm. Aside from encryption and decryption, what else do I need? I need to be able to generate the keys, right? So there should be a key generation algorithm. All of these should run in time polynomial in what? In the security parameter. Okay. So good. So what we need is so let's say that our security parameter is denoted by lambda. Okay. So now what I need is like a key gen algorithm, also often known as simply the setup algorithm. So this will take the security parameter in unary for the reasons that we discussed last time, right? And what does it output? It outputs a public key and a secret key, right? Then there is an encrypt algorithm. So because this is public key encryption, that means that it should only take the public key as input. It takes some message. So this I did not fully specify. So I mean this public key encryption scheme will obviously be associated with some message space, right? And the encryption has to take message from the message space. Okay, and what should it output? Well, it should output some ciphertext, which we call CT. And then there is decrypt. So what this does is that it takes the ciphertext and it takes the secret key and it outputs some candidate message M prime. So what are the two things that we want from this scheme? So one thing that we want is obviously correctness, right? So basically if I ran key generation honestly, I ran encryption honestly and decryption honestly, then it should be the case that I recover the message, right? So I want correctness. right? I won't write it in full formality, but the basic idea is that if keygen enc encrypt and decrypt are run honestly, I should recover M, right. So, basically the probability that M prime is equal to M, right, given that PKSK is output by keygen, CT is output by encrypt, and M prime is output by decrypt. This probability is over the random coins tossed by these different algorithms. Yeah, so that is the probability space. So, this probability should be greater than equal to 1 minus negligible in lambda. So, for simplicity for now you can think of it as just being 1 if you want, but in general we do allow a negligible probability of error. Okay. So, this is correctness. So, what about security? So, there are many ways of defining security. What I will define today is actually not the strongest possible notion, but it's nevertheless an interesting and important notion and very widely studied. So, this is called IND-CPA. So, that stands for indistinguishability under the chosen plain text attack. Okay, so, we will define what this means. So, what we want from security, we will write it formally in a second, but let us discuss for a second what we want, right. So, we would like it to be the case that the attacker has a lot of freedom, right, and even if the attacker chooses its own messages, or it makes queries and gets so queries, I guess, I am sorry, in the public key setting queries will not make sense. In the secret key encryption setting, you can also allow the attacker to get ciphertext for messages of its choice. So, basically the intuitive way of thinking about this is that you have an attacker on the scheme, right. You would like to give this attacker as much information as possible, right. So, for instance, in the public key setting, one of the things that you could allow the attacker is to ask for decryption queries. So, what this means is that maybe I have just seen some ciphertext. Think of an attacker in an institute or an organization, right, what all can it see? So, certainly it can see the public key, right. It may be able to see ciphertext generated by other people, not its own, because its own it anyway knows what is inside it. But let us say one of you generates a ciphertext, and let us say I am the attacker. Maybe if one of you sends a ciphertext to somebody else, maybe I can talk to that person and get a decryption of that ciphertext. So, to model such kinds of attacks, what we allow the adversary in the security game is some kind of access to an oracle. We say that okay, in the secret key setting, because you yourself could not have computed a ciphertext, maybe I will allow you to get ciphertext for whatever messages you want. Okay, now in the public key setting, this particular oracle does not make sense because it is a public key scheme, so I can myself encrypt everything, but there may be a decryption oracle makes sense, that maybe as an adversary I am given access to some oracle that decrypts for me the messages that I choose. Does that make sense? And the idea is So what I am saying is a little bit more general than just security of PKE, that too just in CPA security. You see the definition is actually weaker than what I am saying. But what I am trying to get at is that what would you like in a definition? You would like the attacker to get whatever information it likes, okay, and you would like it to also be able to choose messages of its choice, right? And so now if as the attacker I choose my two favorite messages, okay, M0 and M1, and I ask you for a ciphertext for any one of them. So the only thing I do not know is the bit. You will choose a random bit and give me a ciphertext for either M0 or M1 depending on your bit, okay. The only thing I do not know is this bit. This bit I can guess with probability half, right. So we will ask that if the attacker can guess with probability non-negligibly more than half, then the attacker has broken the scheme, okay. So this will be the idea in general for defining security, okay. Now in terms of int CPA, as it turns out in this particular definition oracles will not come into the picture, but so let me write it for int CPA PKE and then I can discuss a little bit more, okay. So an encryption scheme is said to be in CPA secure. So this is indistinguishability under chosen plain text attack if and only if no PPT adversary A has non-negligible advantage in the following game. So what's the game? So we have some algorithm which we call a challenger. So the challenger generates PKSK using keygen. And gives PK to A. Then A chooses M0 and M1 of the same length. Then the challenger chooses B. And gives CT star is equal to encrypt MB PK to A. So let me be consistent in the order of arguments. And then A outputs B prime in 0 1 and wins if B prime is equal to B. Okay. So let's look at this definition of security. So you can see that this is already an example of a sort of an interactive type definition. Okay, so here it is not just a question of giving the adversary a bunch of things once and for all and then saying, okay, now you distinguish. So why is it that we have this interaction? It's actually to make the adversary as general and as powerful as possible. Okay, so for instance, if I don't give the public key and ask the adversary to output messages, then the public key cannot influence the choice of messages, right? But I would like the adversary to have as much power as it wants. So I will say, fine, I will first give you the public key. At that point you can output the 2 messages, okay. Then I will give you an encryption of a random message and you have to guess. So this is only like this IND CPA security. There is a stronger notion called IND CCA security, like chosen ciphertext attack. In that, the attacker will also be given access to a decryption oracle, where it can also make decryption queries. So this is just, as I said, to capture the idea that the attacker can get everything it wants, so long as it does not ask for, you know, a trivial, it cannot ask for what is B, obviously. So that is the one thing that is hidden from it, right. And as I said, in the secret key setting, you know, even M0 and M1, it can ask for queries from the challenger to get ciphertexts of messages of its choice, including M0 and M1. So in the public key case, it can of course compute all ciphertexts on its own. So why doesn't the following thing work? So I myself know M0 and M1, so why can't I myself encrypt it and decide? I have to figure out this CT star, right? What is this CT star encoding? What is this MB? This is what I have to figure out. So the question is, why can't I myself encrypt both M0 and M1? Anyway, I am in the public key setting. So why can't I encrypt them and then check whether which one gives me CT star? Why doesn't that work? Exactly, it's because encryption is a randomized algorithm. So as I was saying, in the symmetric key case, even if I ask you for encryptions of M0 and M1, no problem, I am allowed to have that information, okay. So the attacker wins if it guesses correctly. So now, as we already discussed, of course it can guess correctly with probability half, right? Yeah. Okay, so the question is, you know, that it seems like, you know, the task of the adversary is to guess the randomness that was used in the encryption. This is what you are pointing, that if you could do that, then you could anyway break it. Yeah, so I mean, the randomness is, let us say the randomness is linear in the security parameter at least. So you have 2 to the lambda possible random strings, right? How will you figure out with better than negligible probability? You can guess and you can succeed with probability 1 over 2 to the lambda, but I am anyway allowing you to break it with that much probability. Okay, so then the response is that then you should use true randomness, good randomness, and yes, indeed, if you use bad randomness, then all bets are off. Yeah, so that's a very good question. So the question is, how will you generate this true randomness? Because you know, most computers, all computers have random number generators which are algorithmic. So that's a very good point. So the way that we generate randomness algorithmically, the reason why we believe it is okay to generate randomness algorithmically is because our adversary is computationally bounded. So we will have to have a guarantee that our randomness is indistinguishable from true randomness, and because this is not a cryptography class, I did not do things like you know, pseudo random functions and symmetric key encryption. But basically a pseudo random function is a function, that a deterministic function, that starting with some random seed will generate computational randomness of, you know, whatever length you want. We did touch upon this a little bit when we talked about symmetric key encryption. So does that answer your question? So basically, you know, the reason that we assume, first of all, we assume that the algorithm will use good randomness. So when we develop our algorithms, we'll just say sample R from this space. Okay. Now, what is implicit there is that when you implement it, right, you may not have a fresh random string, you may be generating it computationally, but in that case you will have to have a guarantee that however you generate it, it is indistinguishable from true randomness. So let's finish this definition. So we defined a game so far, and we said the adversary wins, you know, if it guesses the bit B correctly. And in order to define, you know, the condition when the scheme is called secure, we will say that the scheme is secure if A cannot win the end CPA game with probability non-negligibly better than half. Okay. So, we define the advantage of this adversary as the probability that B prime is equal to B minus half, this absolute value, right, and we want the advantage to be negligible in lambda. Is it clear? Okay, good. So now let's construct PKE. Okay. So we have defined PKE. Let's construct it from the decision Diffie-Hellman assumption and then also from the RSA assumption. Okay, so let me just restate what the decision Diffie-Hellman assumption is. So this is a really nice assumption which has been used a lot. Let G be a cyclic group of prime order Q which is greater than 2 to the lambda. Then the DDH assumption holds if the distributions D0, which is G, G to the A, G to the B, G to the AB, So, we already saw this assumption yesterday, but we did not write it fully down. So, I thought that it's good for us to remind ourselves and write it once again. Okay, so everybody remembers this assumption. Okay, so I have G to the A, G to the B, and the question is to distinguish G to the AB from G to the C, where C is random. Okay, so we saw the Diffie-Hellman key exchange protocol based on this assumption last time.